Are you in charge? Yeah, you guys are in charge. What do we do now? Do we start?
Yeah. All right. Great. I'm very happy to introduce today's Colloquium speaker, Judd Bowman from Arizona State University. Judd did his bachelor's double degree in physics and electrical engineering from Washington University in St. Louis. Spent a couple of years as a computer scientist, systems analyst, both at WashU and then at NASA Ames before going back to MIT to do his PhD thesis with Jack Hewitt. And he's been doing work related to that ever since. Was a Hubble Fellow at Caltech before winding up at Arizona State University in 2010. He's been a professor since. I've known Judd through some of the larger projects we're involved in. He was a project scientist for the Richardson Large Field Array from 2010 to 2015, and now serves as a project scientist for the Hydrogen Ethics Ionization Array for the last 2 years now. But the work he's going to talk about today, the EDGES experiment, the smaller work started as the very last chapter of his PhD thesis back in 2007. So look forward to hearing about the latest results.
Great. Well, thanks, Johnny. And thank you all for having me. This is can you hear me all right? Is this a good volume? Yeah? Okay. So my first trip to Brown, it's been wonderful. It's a beautiful campus, and I think I've eaten more delicious food here in a 2-day period than I have anywhere else recently, so please have me back anytime. I am going to tell you about a project that is related to a lot of work that Johnny and I have worked on together, but completely independent. We're all interested in trying to figure out the formation history of the first stars and galaxies and black holes when the universe was less than 1 billion years old. And we don't have the gumption to go after direct photons from those objects. And we're going to go kind of after their kind of indirect evidence of them. So we're going to kind of skirt around the sort of scene of the crime and see what we can learn about these early objects. And we've been on now kind of a 10-year journey of instrumental development, just trying to build the basic capability to detect the radio signal that we're going to try to use. And so this is a great time to be coming around and giving a talk. We're, I think, at a very exciting juncture where we're finally getting everything clicking and expect that good results are going to start flowing in here any moment. And I'm going to give you a little bit of sort of a precursor preliminary look at what we're getting from this one experiment here called EDGES. So to get started, here's just a quick outline because I felt like I should have one, and so it looks like I spent a lot of time on it. We'll start just by reviewing a little bit of the motivation and then get into specifically the signal, the global redshifted 21 centimeter signal that this experiment is chasing. And then I'll spend the last part of the talk describing the experiment and our latest results. So raise your hand if you've seen this figure before. Okay, maybe less, maybe 10%. Okay, that's not so bad as I feared. I keep judging when I need to stop showing this figure, and when it's become so saturated, people are just going to ready to walk out of the talk the moment they see it. And I'm thinking we're not quite there yet, so good. This is the history of the universe. On the right is all of us living today, and on the left is the cosmic microwave background, so it's clearly an artist's rendering. We don't actually have an observation that looks like this. And so what you can see is, maybe you can see this, all of these early times, right after the Big Bang, the universe was almost entirely hydrogen, and the rest was basically helium. So by mass, it was 75% hydrogen. And then eventually, after some tens or maybe even 100 or so million years, gravity had time to act on some slight overdensities throughout the universe, and some stars and maybe even some galaxy-sized scaled structures started to collapse and form. So these little bubbles up here on this diagram that look kind of like Mickey Mouse's. By the way, I've never had a violet laser pointer before. This is a very big moment for me. It's just rocking my world. All these little bubbles here are supposed to indicate kind of when the first stars, or maybe later on, the bubbles now are supposed to represent galaxies. But the little dots are the stars, and they had radiation come out from them, and predominantly ultraviolet radiation that turned the neutral hydrogen gas, that was the primordial gas, that ionized it, turned it into a plasma. And so as time went on, there's more stars and more galaxies, and they had more time to release ultraviolet radiation. And eventually, all of this neutral hydrogen that was in the early intergalactic medium became ionized. And today, most of the intergalactic medium between galaxies is full of an ionized plasma, the ionized gas. And so eventually, you start to see galaxies that look more like we have today, and they kind of grow and have star formation and end up being Milky Way type things that we see today. So that's the basic history of the universe in a nutshell. And so we have observations from CMB, from cosmic microwave backgrounds, from over here on the left edge of the plot. We have lots and lots of observations from all of modern galactic astronomy that cover galaxies back to about this threshold here. This isn't drawn to scale in time. This threshold here is maybe about 1 billion years after the Big Bang. So there's of order 13 billion years of history here and 1 billion years back here. So we're really pretty well charted on this part of the plot. And we have one data point back here. And so if you want to go from like a baby picture of a human being to a full-formed 35-year-old junior faculty member, you definitely want to at least have a few pictures of them growing up to know how they got there, maybe where they went to college or something. And so that's what we're trying to fill in with the experiments that Johnny and I are working on. And of course, a lot of other people in astrophysics these days are interested in the same, filling in the baby picture adolescence of the universe, right? So when and how that first star formed and what repercussions it had on later formation of structure is a very critical question in this regime. So what do we know? What's the very earliest thing we've seen other than the cosmic microwave background? And I had to go looking because the last time I gave a talk like this was before December of this last year, and this galaxy hadn't been confirmed at its current known redshift. So here's the highest observed redshift galaxy that I know of publicly released, and this is at redshift of 11, which puts this little smudge of light, which is in the Goods North field, I guess right there, puts that little smudge of light, means the stars in that galaxy existed 400 million years after the Big Bang. So we went from no stars to enough stars to be a detectable thing that an existing telescope could see in a short period of time in the scale of the universe, in only 400 million years. So that's pretty amazing. And this is obviously not a normal-looking galaxy by modern-day standards. It has 1% of the mass of the Milky Way, and it has 25 times the star formation. That's how they're able to see it. It's just making stars really tremendously rapidly, so it's making a lot of light. And so that is the oldest thing we've seen. And so what we want to do really is, A, see a lot more things, or at least learn a lot more about what the universe was like at that same time, and ideally start to have observations that push back even closer to the Big Bang from structures that were forming even closer. So that is where we stand. What do we actually know about the very first stars? We know basically what theory can tell us so far. And here's yet another really ancient summary of what we know. On the left describes the properties of the sun, the mass of the sun, its radius, how bright it is, its surface temperature, things that hopefully most people in this room have run across in either a homework assignment or somewhere else, some exciting free reading in the past. The first stars, from a theoretical perspective, because there were no elements really above helium around, they had a harder time, gas had a harder time cooling, which meant that bigger objects were needed to be able to collapse and form stars. More material was needed. So the first stars we expect to be more massive, to be brighter, to be slightly larger, and to be hotter. And that's kind of fundamentally what we know. 13 years ago now, the acceptable ranges of theoretical predictions were that stars could be up to 1,000 solar masses, 1,000 times the mass of the sun. More recent work has brought that number down. The idea that a cloud of gas doesn't have to collapse into only one star. Maybe it fragmented and made a few stars. So nowadays, if you read the most recent literature, the expectations are the most massive. The first star maybe had on an upper bound a mass that was 100 times the mass of our sun, but still almost certainly 10 times the mass of our sun. And similarly with these other numbers, we're more operating kind of on thresholds that were on the left side of some of those numbers. So they didn't have what astronomers call metals. They didn't have heavier elements really above helium. They lived short lives, and then they died. And when stars die, they often form black holes. They may not. Some do, some don't, depending on their mass, depending on their composition. And so we may or may not be getting black holes out of a lot of these stars. And so there that gets us to the connection to what are the, how did the first black holes come into this? And we're going to see in a little bit later that we need things like black holes and compact objects that have matter accreting on them to be able to help us heat the universe, which we think happened in the same time frame. So that's the story as we know it. We'll never, ever, ever see an image of the very first star. It just can't be done. If you think about it, a star is so much smaller than the actual size of a galaxy that they're tiny. The amount of light from one star is insufficient to ever really observe in our lifetimes, maybe many, many years in the future. So if we really want to have the most direct probes of them, we need to go look for collections of stars from as far back as we can. So the very earliest galaxies, which is what James Webb Space Telescope is planning to do, or the fingerprints that these stars leave on the environment around them after they form. And that's what we're trying to do here. So what fingerprints do the first stars leave, and do early stars in general leave? This is a summary from a paper from a few years ago from a theory group that models the formation of early structure. And so on the right is just showing you, each of these little boxes is of the same region, just at different time and plotting different things. So the left column is showing the density of a little 100 kiloparsec region of the universe, very early in the history of the universe, when the first star, about the time the first star would have ignited. So 100 kiloparsecs is roughly the size of the Milky Way galaxy itself, right, for a general sense of scale. And so the first row is when it's 15 million years after that first star formed. The second row is 100 million years after the first star formed. And the bottom row is 300 million years. The first column is just the density of gas, which is mostly hydrogen, almost exclusively. The middle column is how hot the gas is. And the right column is the kind of proliferation of things other than hydrogen and helium. So heavier elements made in that star. And when it dies and explodes, they get released and exploded into the environment around it. And so these are the fundamental fingerprints kind of enshrined on this plot that we're going to be looking for. Early stars and black holes, they heated the environment around them. They had radiation. They made light, ultraviolet light, visible infrared light. That had an initial heating impact on the very local environment. But then when they died, they created shock waves. Some of them formed compact objects from their cores, like black holes or neutron stars. Those may have had accretion disks. Those accretion disks would have created X-rays. And that would have helped to heat a larger part of the global environment around them. When they died, they spewed their heavier elements out. And so the fingerprints we can basically chase are from those three basic factors: the radiation they created, the heating they did, and the metals, the other elements they put into the universe that weren't there before them. And so the ones we're focusing on really most directly in the sort of work we're doing are the heating and the radiation. And the metals that go out lead to different types of stars. Second generation stars would have been different than first. And so when we go to model fitting to things we have to take that we can learn about first and second generation of stars eventually one day. But kind of the most immediate thing we see is the heating and the ultraviolet light getting into the rest of the universe. So what Johnny and I work on in the context of other projects is really focused on understanding how this ultraviolet light gets released in the rest of the universe as more and more stars and galaxies form. And so this is just an artistic rendering of a simulation of an ionization front, ultraviolet light going away from early objects out into the distant gas between galaxies and turning that gas into ionization. And so that's just wrapping up kind of the third third pillar of fingerprints that we're going to go looking for in our general crime scene here. So you have Johnny here at Brown, and so you may have heard the spiel about, and you may have taken a class that talks about how you get radio waves from hydrogen atoms. How many of you guys have talked about hydrogen hyperfine lines in some quantum course or something like that? And a few folks, grad students, probably have gotten there. Maybe has it come up on a qualifying exam? Is that a good qualifying exam question? You wait until Johnny starts writing them. So what we're basically doing is we're going to look for radio waves from hydrogen atoms, and they're going to be radio waves that come from the hyperfine spin flip transition. So this is the quantum properties of the electron and proton in a hydrogen atom. If the spin state of each of those particles is aligned, it's a slightly higher energy state than if it's anti-aligned. And so depending on the background radiation field and the local thermodynamic environment, you can either get emission of that line wavelength, of that energy level wavelength. And that happens to be at a radio wavelength, and that's 21 centimeters, which is widely used in astronomy to detect hydrogen gas all throughout our own galaxy and many others. This is a bunch of math, which I really just put up here in case anyone felt like asking questions. But the fundamental way we're going to describe it is, I feel like I've lost my wonderful ultraviolet pointer. Can you guys see it? you can see it. Oh, I see it now. Okay. We're going to describe how strong that line can be with this parameter T sub s. It's the spin temperature. And what's relevant is that number compared to any background light we're seeing. And because we're going to be looking for gas that's all out throughout the universe in between galaxies, the background light that's relevant for us is the cosmic microwave background. And the temperature of that radiation field at the time in the universe when we're interested in studying the gas. And so basically one of two states can happen. The gas, this temperature from this line balance can either be above or below the background light. And so we can either see it in emission or absorption. And the temperature of that line is highly determined by a few things like how dense the actual gas is in the universe at that time. It can be coupled to the actual kinetic temperature of gas when the gas is really dense. When the universe is less dense, that line temperature can be driven to more of the general radiation field kind of black body temperature. And then at other times when stars kick in, their ultraviolet light can, through other radiative processes that we're not going to go into, move this spin temperature effect down back to kind of a kinetic gas temperature, so they can kind of adjust where it equalizes to. And so we're going to be heavily reliant on this spin temperature as our most fundamental tracer of what the properties of the gas are that we're trying to see. And then we're going to go through that parameter, backtrack through modeling to what the first stars would have had to be like in order to have driven that temperature to certain numbers. So it's a very important parameter. The other very important parameter is how much of the gas it was neutral at any given time in the history of the universe. So if it was ionized or not. If it was ionized, we don't get this emission. If the electron is no longer part of the atom, there's no chance for this hyperfine line to happen. And so there's no chance to get any signal from this hydrogen atom. So the amount of stuff that's still neutral atoms and then the spin temperature are the two fundamental properties that we have to interpret, that we're trying to observe and then interpret everything through. So if you go and trace the history of the universe here, on the right now is when the Big Bang, on the far right off the plot would have been the Big Bang, and on the very left of the plot is today. And this is plotting a few of these temperatures that we're interested in. So you see on here are three basic lines. There's the CMB temperature, so the microwave background temperature, which is cooling with like 1 plus Z, like as you come down in redshift closer to today. Then there's the kinetic temperature of just gas in the universe, which is cooling adiabatically as the universe expands. It cools faster than just the CMB radiation. And then there's the spin temperature that we're interested in. That is something that's more of a measurable, observable for us. And so initially, early on, the universe is very dense, and all this kinetic gas is causing the spin temperature, all this collisions in the gas are causing the spin temperature to be kind of balanced like the gas temperature. So you can see up front at the right side that the spin temperature is on the dashed line. As the universe gets less and less dense, it starts to wander away from it and eventually gets kind of coupled more tightly to the CMB temperature. This last little blip here before it shoots off the screen, so this last little blip right about here is when stars must have formed in this particular theory model, and their ultraviolet light caused the spin temperature to get driven back towards the gas temperature. And then ultimately in their model, the stars died and made X-rays from their leftover compact objects like black holes, and that heated all the gas, and the spin temperature just stayed kind of coupled to that hot gas as it got heated. This is the basic temperature profile from kind of basic astrophysical theory that we expect to see. If you factor onto that the ultraviolet light from those first early generations of stars ionizing some of that gas, you have a whole bunch of, this is the ionization fraction here, so a whole bunch of neutral gas, and at some point that gas gets ionized. Here's 3 different scenarios for 3 different models, and now the gas is 100% ionized at more recent times in the history of the universe. From the previous slide, you know that if we multiply some of those numbers together, we're going to get the signal that we can actually observe. So this is the brightness temperature of the 21 centimeter line, and as it goes through time, you see there's some times when it should be seen as an absorption relative to the background. This dashed line here is the background cosmic microwave background temperature. So there are times in the history of the universe, if we look out at a wavelength that corresponds to this redshift for the 21 centimeter line, we should see this signal as absorbing some of the background CMB. At a more recent time, the redshift 20, when the first stars were kicking in, we see another time when it's absorbing the background CMB light. And then as galaxies are getting to be more fully formed and the gas is all hot, in between galaxies, then it was an emission, and eventually the ionization of all of the neutral gas makes the signal go away. So this kind of squiggly S is an observable feature we should be able to see in the radio spectrum. And the radio spectrum, you take redshift down here, and you take a 21 centimeter line, and you multiply it by 1 plus its redshift, and that gives you the wavelength that we can look at and try to see the signal from that appropriate redshift in the history of the universe. So plotted in frequency up here, we're looking down basically where you're watching TV and listening to FM radio. 100 megahertz is right here in the center of where we're trying to look, and that's exactly where your FM radio band is. Right? So this is, by radio standards, a very long wavelength compared to what most radio astronomers look at. So the experiment I'm going to tell you about, EDGES, has two parts. I just wanted to recast this again. We're going to divide our experiment into two bands and try to do the part that's above 100 megahertz separately from the part that's below, and we're not going to try to tackle this very low frequency, very high redshift component over here. We just don't think we have the ability to do it yet. So I think we just talked through these different mechanisms, what's happening at different times on this history. So there you can see EDGES is one of a few experiments trying to make this particular measurement. What Johnny and I work on, and some of the folks in his group, we work on also some large arrays like HERA and PAPER and MWA, and eventually the square kilometer array. And they're trying to make maps of the sky from the same era and try to get out the same science by looking at the statistics in those maps. For EDGES, we're just trying to measure the spectrum. And that spectrum encodes quite a bit of information about early stars and galaxies. So the way it encodes it is by the amount of X-ray light and amount of ultraviolet light that the theoretical models for those objects create. And so this plot is showing just theoretical predictions of some of these for different types of stars, different masses of stars, different assumptions about what the properties of these early stars were like. And if you assume that they make not very many X-rays, then the signal we're looking for has this big absorption feature, and it lasts a long time until much later in the universe. If you assume that those early stars die early and make lots of X-rays, whatever black holes they may form make a lot of X-rays, then you get this blue curve down here, and you get the signal getting, the gas getting heated sooner, and our signal coming into an emission relative to the background sooner. Similarly, if you think they make a lot of ultraviolet light, they crank down the spin temperature to make us see this absorption trough sooner than we would have if they didn't make a lot of ultraviolet light. And if they make only a little bit of ultraviolet light, they never really crank down that spin temperature to be matching the kinetic temperature, and so we never see this absorption feature. We have to wait until they heat the gas, and then we can maybe see some emission. And so what we want to do is go out and measure what actual curve we have. What actual curve we have from trying to measure the spectrum, and then we can map through the models back to what the properties of these early objects were. So there's our indirect search aspect of this again. And don't think that the theorists have only made a few curves. They've made literally hundreds, maybe thousands of them by now by tweaking every knob they can think of. And so here's just one plot, all showing a bunch of them on one to see kind of the family of signatures we might be looking for. And again, you see they range from the ones that have no X-rays, or at least very late coming X-rays to heat down here, and the ones that have a lot of ultraviolet light coming to make the early trough up here. And then reionization makes all these signals eventually go away. So they all share a lot of common properties that we can hope to back out one day. So it looks really straightforward. We're trying to detect a signal that's about 100 millikelvin, 25 millikelvin to 100 millikelvin. We're trying to do it in a part of the radio band that astronomers first used almost 100 years ago when they first started making radio telescopes. They were here at these frequencies. The field in the 60s rapidly moved away from them because it turns out there's problems down here when you try to study things astronomically. But we're coming back, and we're coming back with a vengeance these days. And so we only have to deal with one small little problem that makes life incredibly, incredibly hard. And that problem is our own galaxy makes a ton of radio waves from synchrotron emission, which is the electrons spinning around the magnetic field of the galaxy. And it's incredibly, incredibly bright. So our own galaxy at these wavelengths is making synchrotron emission that has a brightness temperature equivalent to anywhere from 100 to 10,000 Kelvin. And we're looking for something that's more on the order of 10 millikelvin. And so we have at least a factor of 10 to the 4 between all of the power coming into our telescopes and the actual thing we're looking for. So we're looking for a tiny little squiggle in a spectrum that is about 0.01% of the total amplitude of that spectrum. So it's a high precision game to try to make an instrument that can not take all of that power coming from our own galactic radio emission and do something we don't realize the instrument's doing and make it look like this signal that we're trying to find. Because that'd be very easy to do at 0.01%. You imagine you might not have your instrument calibrated at 99.99%, and all of a sudden now you've made something that mimics what you think you're looking for or otherwise corrupts it. So the name of the game is to build an instrument that can not do that. And that's what we've been trying to do for the last 10 years. So that instrument is EDGES. The experiment detects the global 21 centimeter signature, so that little squiggle in the plots. And the team is quite small. It's me, one retired, some of you may know Alan Rogers. He's one of the real kind of fathers of radio astronomy. He's retired these days, but he really helped get VLBI off the ground a number of years ago. He also was one of the first people to work on triangulating your cell phone position based on all of the cell phone tower, what they know about you. So you can thank Alan for some of the early algorithms for your cell phone location when you don't actually have GPS. But he still is kicking along, helping us. He's one of the main people intellectually on this project. We have 2 grad students, Nivedita, who just started, and Tom, who's about finishing, and 1 postdoc who was working in my group up until this year and went off to another institution. So the 5 of us are doing our best to do this experiment, and we've been, I think we're at a really good point, which is why I wanted to start coming and talking to all you guys about it. So we had to go find somewhere where there isn't radio pollution, and there's only a few really good places on the planet to do that. Johnny has spent a lot of time working at one in South Africa. We are working at one in Western Australia called the Murchison Radio Astronomy Observatory. So our instrument is under that dot on this map. And if you've ever been to Australia, Perth is around here. That's the kind of San Diego of Australia. There aren't really any other major towns on this coast until you get up to like, I don't know, some other stuff up here. Sydney and everything that you think of is over here on the East Coast. And so we're out away from people, and that's good because if there are no people, it's not profitable to have a TV station or an FM radio station. And so they don't. And so we spent the first few years, we had to just get our bearings. We didn't know where to go, how to do this, what was going to work. When we started this project, the best anyone had ever made a radio receiver and calibrated it was to about 1% accuracy. And we knew we needed to get to about 0.01%. So we had to do 2 orders of magnitude better than any documented radio receiver at the time. And so we just kept going at it. Oh, I've got a plethora of pointer options now. Thank you. You guys are well equipped. Thank you. So we had this exploratory project, and here's what our experiment looked like for the first few years. This is an antenna, this little, we call it a 4-point antenna. These are based on a dipole, which you may have also studied in a physics or E&M class at some time. We're also in an engineering building. Are there electrical engineers in this building? Or just mechanical? Or yeah. And underneath in this grocery store bag is our radio receiver, which I'll show you some images of our current one in a little bit. And that was a last-minute grocery store bag purchase to keep the rain off of it when I was out there one time. And that is duct tape holding the grocery store bag on right there. You can't see it, but we're over a piece of rolled-out chicken wire so that our dipole antenna looks at the sky and not into the ground. And the Australians kindly provided us with some solar power and a place to put our equipment back here. This blue line, which would maybe only be of interest to Johnny, is the fiber running to the MWA, which was out there quite early in those days. And so we went out there just with this really low-budget experiment and just to see what we could do. And we didn't know a lot, but we knew that we had one design principle, which was if you want to keep any of this really strong foreground power from getting corrupted into something that looks like that squiggle of the signature we're trying to find, one way we could probably do it was to keep our entire design of our radio receiver and our antenna electrically small. If you have something that's electrically small, like smaller than a wavelength, like this dipole antenna here is smaller than 1 wavelength at the frequency range we're looking at, then if it is causing any structure, that structure is going to have a long period in the spectrum. And so we were just going to take our best attempt to push any systematic structure caused by our instrument into long spectral periods. And long spectral periods probably aren't going to look like that little squiggle that we just saw all these theory calculations. That was the best anyone could think of to do at that time. And so keep it small, keep it simple. Don't try to calibrate because you have to do 2 orders of magnitude better than we knew how to do. We didn't know where to put it. We didn't know if all this foreground power was going to be cooperative. The atmosphere of the Earth starts to gets opaque if you go to low enough radio frequencies. We're going to be getting kind of close to that, but we were worried about what effect that might have. And so we had a bunch of open questions. And so we learned a lot with this experiment. We managed to make a really nice observation here. So this was its best integration, and this is the spectrum it observed. And again, you can see the total power here is in the hundreds of kelvins. These little spikes are from radio transmitters from mostly satellites and airplanes that even when you go out to the middle of nowhere, you can't escape the fact that airplanes fly over you. And so fortunately, we can basically know what frequencies those were coming at and eliminate them from our analysis. But otherwise, you see a really smooth curve here. It doesn't look quite like that really nice power law that we saw of the foreground power. And that's because we weren't actually calibrating our observations. So we weren't trying to compensate for the fact that the receiver was less sensitive over here than it is in the middle of the band. And so we just lived with it. And we were going to try to look for little squiggles in this thing. And we fit some models, and we were able to rule out basically any little squiggle that looked like an actual step function. But it was a squiggle of the right amplitude, but it just meant that it had really sharp edges, and we could rule out something with really sharp edges. Now you see where the name of the project came from. And so it wasn't very interesting astrophysically, but it was a pretty big accomplishment technically. And so we were happy by that, and that was successful in getting us more grant money to keep trying, so that was a good step. We had a nice paper in Nature from it. And we learned all the important lessons we needed to learn. One was you're not going to get there by not calibrating your instrument. It's just you need to actually bite the bullet and figure out how to calibrate your receiver better. We learned that there's a lot of interesting science at the higher redshifts that in that early precursor kind of experiment we weren't trying to get, so we were going to go build 2 instruments in our next try. And we learned that the antenna itself can also make little squiggly things in your spectrum. And so you need to actually be able to understand your antenna or correct for it to really high degree of precision as well, in which that we had not taken into account initially. So we learned all these important things, and we redoubled, and we came up with like a calibration strategy of building just a standard radio receiver like you would have in the 1950s. And inside that receiver, we have a switch so that electrically the amplifier and the receiver can look at either the antenna or at a hot load or a cold load. And so we can do some internal calibration of the receiver and make sure it's operating very stably and get rid of kind of first order instrumental properties, instrumental effects. Then to do a much better calibration, we needed to attach things to our radio receiver that we knew what they were. Right? That's how you do any calibration. You need to look at something that you know what it is. And ideally, a number of things that you know what they are that have slightly different properties to make sure you're doing a robust correction from what you get to what you see. And we do that in the lab with physical things we can model physically. Very, very simple things that have very first order, really highly accurate ways to model them, like an open length of cable, 8 meters of cable. We just put it in the lab, and we connect that to our radio receiver, and we can model to very high precision what that should look like to our receiver. Then we put a short across the end of the cable, and that should look slightly different. The phase of any reflected power in that cable should now be inverted, and we can see if that's consistent. Then that helps us get one aspect of our calibration, and then we do other things like put things that make noise, electrical noise, like we put hot resistors and connect it to our receiver and stuff like that at various temperatures. And through doing we do this for a period of weeks after we build a receiver and before we ever deploy it out in the field, and we end up getting some really nicely calibrated spectra that are at this basically 0.01% level. So with all of that knowledge in hand and some good laboratory work on understanding how you can calibrate your receiver, we built a new experiment, and so we call it, when we are not lazy, Edges 2. And so here you can see, and we also have 2 antennas now. This is one that targets that high band. That's a little bit higher frequency range. This is a bigger antenna that targets a little bit lower, higher redshift range. Our site moved a little bit out in Australia, but we still have a little hut with power. That is a part of the ASCAP. It's an SKA precursor telescope the Australians are building. It has nothing to do with us other than we steal power and internet from them. And so we have a nice new experiment. You can see we have a much bigger, basically, piece of metal underneath our antenna. We extend that even more with wire mesh. All of this helps the antenna have a more stable beam in frequency. I'm going to talk a bit more about that. Here's our receiver. From the outside, it's really boring. It's just a metal box. It's about 1 foot by 1 foot, so kind of like a shoebox. We stick it in this little trap door underneath our antenna, and it connects. This is called a balance, basically a transmission line that goes from our receiver up to the antenna. And then in the hut, we just throw in a couple computers and digitizer cards and a few other environmental sensors. And we're off and running again with our new and improved experiment. So it's still a very, very simple experiment. If you take the lid off the receiver, it's still pretty boring. We have an input. This is the port where we connect back to our hut. So that's where the signal leaves the receiver. This is where we connect to the antenna up here. This is a mechanical switch that lets us either have our low noise amplifier, which is hiding in this box, go, and this is our main electrical path when we're doing science. The signal comes from the antenna through the amplifier, through some other amplification down here and out the back. When we're trying to calibrate more, we need to look and measure the impedance of our antenna, and we need to do it in the field in situ. And so we have the switch here so that we can actually run through a vector network analyzer, which is a big piece of electrical equipment that is used commonly to measure the impedance, the phase and amplitude of impedance of an object. And so we can switch that in and measure our impedance of our antenna. Underneath, we just blow a bunch of air through conduit underground, and we have, this is the temperature controlled, so we have some thermoelectric plates dissipating their heat down there. In the lab, the sources, so I said we just connect a long cable to it. So here's a long cable coiled up in a box with one port coming out, and we connect that to the front of our receiver. That's one of our calibration standards. Here is basically a resistor that we heat up, and it gets connected through a little bit of piping, transmission line, and then to our receiver as one of our other calibration standards. So believe it or not, like to take the time and effort that we did was kind of novel to make these really calibration standards that could be reliable. And so that was kind of one of the things that people weren't doing when we started this. When we spend weeks in the lab before we take the receiver out to the field, it looks like this, just sitting there getting calibrated. We connect the various, these are various of those calibrator sources, go one after another on the front. I'm going to skip this in the interest of details. When we want to prove that it works, we wanted to prove that we absolutely knew the temperature of what we put into it and use an input that looked a lot like what the sky is going to look like when you connect it to an antenna. This is a tungsten light bulb, a tungsten filament light bulb. It has a nice property that when you turn it on, it gets hot. And it's like a resistor getting hot. And so you can look at the radio, the electrical noise coming out of that, which we propagate just through some kind of impedance matching circuitry. And we can see if you measure the current going through the light bulb, you know what temperature it should be. There's models for that. And we can measure what our receiver tells us the temperature is. And so if you look at it, you get a raw measurement, and it's this wavy line down here. And we can apply some of our calibration corrections, and we apply some more calibration corrections. And we end up getting this final line here, which looks a little bit wavy on the screen, but it's actually really quite flat on the computer screen. And we know it to within, in an absolute sense, to within a couple Kelvin, and to, after a little bit of trickery, to within 100 millikelvin. So we're at roughly, and this 100 millikelvin is the relevant number for what we're trying to do. And so we're within a part in 10,000 of knowing how hot something is that we look at. So that was a big accomplishment for us. The last thing we had to do was realize that our original antenna design, which was this thing here, was imparting too much structure into our observed spectra. It was also attracting the emus. They really liked it for some reason. And so did the flies, but they like anything out there. So that's why we wear fly nets. And so we redesigned our antenna, and we went from this very highly complicated diagonally shaped antenna, and I'm saying that kind of like as sarcastically. But we did go to an even simpler antenna, which was just squares, basically. And believe it or not, that antenna has a much better control of its beam pattern over the wavelength range. Radiation basically bounces around in it less than it does for the other antenna, is one way to look at it. And the what? And the emu doesn't seem to come back anymore. Although now there are some kangaroos that like to sleep under one of them, so that's a bit of a problem. Let's skip by the details. So here's our new antenna. The last piece was the other way you have to make, if you want your antenna's radiation pattern, the part of the sky that it's sensitive to, not to change too much, you ideally would put your antenna over an infinite metal surface. That would be one of the best ways to have an ideal dipole over an infinite conductor. And as you can see in this, our early deployment, we only had about a wavelength of reflector underneath, of metal mesh underneath. And so earlier this year, we extended that. And it looks like this kind of jester's hat, because I put rocks on the edges so they wouldn't catch us and kill us. But we made it to a much bigger, 550% increased area ground plane, which improved the properties even more. And even got my wife Cassie out here, who learned how to weld on the job there, and then proceeded to make like thousands of welds over a nonstop 7 days of welding. And she still loves me, so it all worked out okay. I connected all of these clamps, because we had to get all these little wire meshes in the right alignment to weld them. I ended up having like this clam claw of a hand after the end of the week, like those crabs on the beach. Maybe they have them around here, I don't know. We don't have them in Phoenix. If you look just at the bottom row of each of these, this little wiggle is what our spectrum looked like from one of these instruments before we extended its ground plane, and it had an RMS, these little wiggles after we tried to remove the foreground. It had an RMS originally of 180 millikelvin. We extended the ground plane and did the exact same thing, and the RMS went down to 68. So all of these wiggles were coming from the fact that we had this small metal ground plane and not a big enough. We ideally would go even bigger, but I don't think I could convince my wife to go out and weld that much more metal. So we're going to stick with what we have. So in the last maybe 10 minutes, I want to tell you where we stand in our results from this project. And this is all preliminary. We're writing the papers as we speak. And so in some of these plots, we've stamped preliminary on them, and others I didn't bother, but they may change just a little bit before you see them published. So here's 100 hours of data, and what I'm only going to show you now is from that high band instrument, the smaller of the two antennas. So here's 100 hours of data observing. This is basically the foregrounds of the sky, because that's just what you see by eye. It's beautifully smooth by eye. If you fit a fifth order polynomial to this, and you look at the residual to that fit, these are the wiggles that are left. And we have about 16 millikelvin wiggles in there. And we're looking for a signature that's of order 20, anywhere from 0 to 100, or even maybe larger, millikelvin. So we're in the right ballpark. All right, that's what you take away from this figure. So what we're going to do now is do a parameter estimation on that data, and we're going to simultaneously fit the nuisance terms that we need to accommodate the foreground signal at the same time as we fit 20 models for the global 21 centimeter signature. And we're going to look at a couple different cases. The first one is going to be cases that have a fundamental assumption that the part of the history that we're looking at here, which is above 100 megahertz, so kind of around redshift 14 or 13 to about redshift 6 or 7. So the data we have spans this range here. We're going to look at a class of models that fundamentally assume that the gas in the universe is hot then. And that's very simple because we can model the signal we expect to see just as this sloping transition in one scenario. And so we can model that as a hyperbolic tangent function. It's nice, it's analytical, it's easy to work with. So we'll start with that. I'll show you a couple of plots on that. And then after that, we're going to look at a class of models that had basically no X-ray heating or very late X-ray heating. And they're really handy because they're a much bigger signature, and they leak all the way up into the times when we have the data we're looking at right now. And so Johnny's looked at models like this with some of his paper data. We're looking at them right now with edges. And then I'm going to end with one model that makes me really, really happy. So it's a very limited sample because it's just one model where we can kind of look at the entire evolutionary history all with this current data, just as a fluke of a model. But I like it because I think, well, it's good for us. So here's a bunch of hyperbolic tangents. They go from some emission on one side to no emission on the other side. And you can tweak where they fall, at what redshift that halfway crossing point is. Just here's the equation. Here's your middle redshift. That's a parameter you can use. And you can use the parameterized so that we can see how fast. Like you can see this one happen very quickly. These over here are maybe a little bit more gradually. That's just another parameter in the model that we can fit for or tune. In this case, fit for or constrain. And so that's our signal model in this one class of models. It has an amplitude given by cosmology here. So the overall amplitude is set by cosmology under the assumption that the gas is hot. And then our foreground model is a particular type of polynomial that we use. We call it the edges polynomial. And all it is a standard polynomial, but with a factor of to the frequency of the minus 2.5 in front. So this is in frequency units. And that's just because the actual foreground has a power law index of around minus 2.5, so we might as well just kind of condition our own terms to be close around there. It makes it have better fits with fewer orders, polynomial orders. So we're going to go constrain all these parameters and see what we can get. And what we get is this. Here, so we're going to sweep over all those hyperbolic tangents. We're going to sweep over a range of redshifts, and we're going to constrain how long, if ionization happened at that redshift, how long could it have lasted? And we're really good at ruling out things that happen quickly, and we're really bad at ruling out things that happen slowly. And so our eliminated parameter space, so here's how long reionization may have lasted, and here it is only in frequency, but this is essentially redshift. So here's redshift 13, and here's redshift 6. And you can see this is 95% confidence exclusion zone, so all this area down below that curve is ruled out at 95% confidence. And here's the 1 sigma, basically, so here's 68% confidence. So we're ruling out reionization, so the end of this signature, if it went away really fast, we're ruling that out at high confidence. If it went away at a more common speed that you see in more of the models, we're starting to get into that at our 1 sigma level. So standing on its own, it's kind of hard to make sense of this. If you put it in context with other astrophysical constraints, here now I've done it at redshift on the bottom, so again, kind of roughly the same as the previous plot. This was a slightly different run on a slightly different piece of data, and I didn't have time to update this plot, but it's roughly the same level of 95% confidence. And then here I've plotted just a big swoop that's roughly the level of our 1 sigma era from the previous plot. And so we're ruling out things down here really well, things up to here in a questionable but tantalizingly encouraging sense. And if you look at other astrophysical experiments, we know from the Planck CMB experiment that reionization, the midpoint was probably around redshift 8.8. That's their best fit. But their error bars span this white region over here, from here to here. We know that from galaxies, observations of individual galaxies, that the universe is probably pretty neutral, pretty ionized by the time you get out here to redshift 6 or 6.5. And from some other, just how long, if you move up on this duration phase space here, you get kind of an angled constraint. So we know that everything up in this top right corner is probably ruled out from other astrophysical observations. And the kinetic Sinyaev-Zeldovich effect tells us that reionization probably didn't take too long. And depending on how you work the data, the constraint is an upper bound up here that either reionization was faster than a redshift interval of about 4, or if you kind of work it in a more optimistic, or if you want to call it that sense, you might push their constraints down to almost 2.5. So this kind of white region in here is the allowed time when reionization happened, which would be left to right, and how long it lasted, which would be up and down. If you take all the best set of data, excluding the edges data because it's not yet published, and you see what's the best fit for how long this era lasted, everything we know about star formation, and roll in the theory of what the first and early stars and some assumptions about early black holes and things, and fit from all the existing constraints, you get kind of a series of best case fits that are on this little kind of streak here, all from this one paper with different assumptions. And so the really exciting thing to me is that the edges 1 sigma result is now just almost to the point where we're pushing up to that, what the theorist, what the best fit of all the constraints says probably the signature actually looks like. So we're within the ballpark of actually getting to the point where we're going to detect it if all this is true. Okay. Now we're going to jump to the assumption that all of the gas in the universe is cold at the time that we're going to do our model fitting, and look at just another whole class of models. These are all models where you have this big absorption signature, and when reionization is happening, the gas is still cold. So low or late onset of heating from the early population of sources. And so these are models we can rule out with our first look at our current data. And so they're just a handful of models. All that they share in common is that X-rays were either very little or very late onset in the models. Here's a paper that we really like because the author purposely made a bunch of models that he thought we could rule out, or that this type of experiment could, and sure enough, we ruled them all out. And so that's gratifying to us who have spent 10 years with not any real results, and so now we can at least rule out an entire paper. So that's very exciting. And all of this work I'm showing you here is by our postdoc, Raoul, so watch for his name on the papers in the next few months. Okay, and our final constraint, the one I'm most excited about, is this model by Nick Nedden and I think one of his students. And the reason I like it is because they took all their best guesses, what they know from modern day astrophysical sources, what the radiation they put out is like, how much escapes their galaxies and things. They used the Starburst 99 model to get most of that. And they put in some of their own particular group's research on shock heating. So when you have a star die and explode into its environment, the shock that it creates will do some heating. And they have their own particular take on that. And they made what they're calling their absolute best guess for what this 21 centimeter signal should be like. They're kind of putting their stake in the sand and saying, given everything we know now and all the work our group does, this is what we think it should be. They weren't trying to really tune the parameters. They were just trying to get the one model they thought was most likely. And we got lucky because that model happens to have some of this absorption signature and some of this emission signature in the band that our high band is observing. And so it's a very fortuitous event that we get this very clear, all of the signature into one of our instrument's bands. And we don't have to use both bands to try to constrain it. And so we've been working on this one. And it's not yet quite time to say with any number behind this. But the hint that is strong enough for me to say it in a talk is that we can rule out their best guess at what this signature is. And what we learn from that, we don't know yet because we haven't gotten far enough in our analysis to actually start tying back to the underlying astrophysics. But I think it's going to be really exciting that now that we can actually start to do this on a whole suites of models, and at least one where we get kind of a comprehensive look at what was predicted, all from one band. So where are we headed next? Well, now we just can't quit adding instruments. And so here's a Google Earth view of our trailer, our current low-band instrument, and our current high-band instrument. I'm heading out on Saturday for a 3-week trip. And sometime before Saturday, the Australians are going to dig a 100-meter trench for me from our hut out. And I'm going to install another antenna out here. And we're going to observe with 2 low-band instruments at the same time and try to confirm and rule out some of our systematic effects before we start doing our next layer of analysis on that data, that low-band instrument data. So my wife is going to be back in service doing some more welding. She's really looking forward to it. And you can see we even have plans for yet another installation, but we have yet to put a date behind that one. And I don't think it would be a very good thing for me to do at this time. So that's where we stand on this project. We've come a long way in 10 years. We're actually, just like with the arrays, getting to the point where we're doing science. We are looking for these fingerprints of these early objects, and we're actually now at least in the right room and probably have the right size magnifying glass. And Sherlock Holmes will probably be pretty proud of us. And so I think any year or month now, we're going to start to have this sort of really exciting sort of actual tied into astrophysics for the first time. And so that's our status update. We're happy, we're excited. I hope I can come back with some really good news in a few months' time and let you all hear it again. And so thanks for listening. I appreciate it. That's the end.
Time for some questions.
Yeah. Or you want to call?
Please,
Okay.
Yeah.
So there were, I mean, of course, your talk was very nicely arranged. There was a lot of technical, description. It was very cool. Except I have some theory questions.
Uh-oh.
I have 2 questions. I think so. You mentioned in the end, like there are these 3 categories of models that you can potentially rule out or you can probe. But all these assume that these are astrophysical sources of reionization, right? So there's a big assumption there.
Mm-hmm.
I've not read about the theory of how reionization happened, but I know that it's still a big black box. We don't know whether there are any exotic sources of reionization.
Yeah.
So how does I think the low band edges could maybe...
The low band edge, yeah. So so that's true. Everything that I showed as constraints has the assumption that there's no exotic physics. No dark matter annihilation, no black hole evaporation, changing the fundamental stellar models that go into these curves. That would throw a wrench on everything. And so, yeah, we're operating under that assumption for now. There are potentially, if you take some really extreme scenarios, there are potentially observable effects from some of those more exotic ideas. The one that I remember, because I, for a while, was kind of gung-ho to try to constrain it, was if you had a whole bunch of black holes of just the right mass and only one mass formed in the Big Bang, and they all evaporated at whatever redshift was, pick a redshift in our band, redshift 15, you would get a nice, beautiful spike, and it would heat the IgM nicely, beautifully, in a nice spike. Really well-defined feature, because all the black holes would evaporate all at the same time. And it was a really contrived idea. But I just loved it because it would be something we could easily see. I don't know, as we go farther down this road with the arrays and with edges, I suppose at some point we're going to need to think more seriously about what that exotic physics could do in the case of all of what we think we're constraining. Yeah.
No, I mean, of course, exotic physics is like a convenient placeholder, but what I'm really interested, the essence of the question is, is a step reionization natural? Of course,
Yeah.
you're experts,
Yeah.
What's the preference?
The step is not natural, but you can see this general broad class is natural. So if you have anything that's going to heat the IgM slowly or release ultraviolet light over a period of time, and it has to travel the distance between galaxies, anything that's kind of coming from a a distribution of stuff, right? Whether they're small galaxies or something else that isn't so stellar. But if it comes from a population of things that kind of have a stochastic period of when they're going to do stuff, you tend to get these gradual shapes, right? And so that is, I think, a pretty fundamental nature of all the modeling. But again, you can see there's some that don't have the dip and others that do, and some that never have the emission and others that do. And all of that, I think, is highly dependent on what the physics is you put in. And that could be non-stellar physics. Yeah.
Okay, and I have another question. Sorry for the question. But where does advanced LIGO, have you considered how does that fit into things?
No, we have not gone that far in our thinking. I doubt anyone is in the 21 centimeter community is worrying. Yeah, so you're saying, okay, now we know there's 30 solar mass black holes out there,
right.
Possibly more than we ever would have thought because that's the first thing we saw.
Yeah.
Does that affect what we assume these early the first black holes that formed might have been like?
Right.
That's definitely on people's minds. But I don't know of anything to this point that has concrete expectation for that. Yeah.
Thank you so much.
Absolutely. Yeah.
You mentioned before that
You want a microphone? There's a microphone right by you.
Oh, thank you. You mentioned before that your early experiment was ignoring the effect of the ionosphere.
Yeah.
Or trying to see what that might be. I'm just curious what sort of effect you'd expect the ionosphere to have on global signal measurement.
Right. So what effect do we expect the ionosphere to have on this measurement? In our high band, we don't expect very much signature effect because, so the ionosphere has two basic effects at these radio wavelengths. It blurs what you see on the sky, and it also then can absorb some of the signal coming from astronomically. So because we're averaging over a whole bunch of the sky, we don't care about the blurring of any part of the sky too much. That has no effect on us. But the absorbing some of the input power is a major potential concern. And that would cause potential other wiggles in the spectrum. So we've modeled it. The ionosphere is relatively well known, understood. And so at that kind of macroscopic level of the ionosphere, we can model, how much, what the electron content is. There's through GPS measurements, through there's big community of global people modeling this. And so in our low band, it is something to think about, and it provides yet another very broad, slowly changing kind of shape that could be kind of imprinted or multiplied on the foreground signature, which then may or may not end up in our kind of residuals after we fit our nuisance terms. So we've looked at that pretty extensively, and we think that our nuisance model for the foregrounds can soak up any potential realistic ionosphere effect. And so we actually have a paper out where we measured the electron temperature in the ionosphere from our own data by fitting actual ionospheric component model as opposed to our kind of more generic nuisance terms. And it looked like it was pretty good. So one of the ancillary pieces of science that EDGES could do is it's called a rheometer. If you have a broadband radio instrument that just watches the sky night after night after night and looks for times when more or less power gets through, that's exactly what atmospheric scientists do to measure aspects of the ionosphere. EDGES is really good at it. We're a very broadband, very highly calibrated rheometer. We just don't care. So it's a shame on that standpoint, but we did take one little detour to write a paper about it. Yeah. Any other questions? Yeah.
So I wanted to ask about the connection on the other end with individual sources.
Mm-hmm.
Because one of the things JWST is going to be doing is going after emission and measurement of the population of objects at redshift 8, 10, in the middle of the EDGES band.
Mm-hmm.
Have you thought about how to fold in the information about the population and emission of those measurements like star formation? That could feed into ruling out certain models.
Absolutely. And so Johnny's done some of the early, current work on this, where he's worked with the theorists. They have ways they parameterize these stellar models, and we're working even, more and more to try to make those parameterizations compatible with the type of observations we're going to get and what the galactic observers would like to naturally use for the type of observations they get. And so it's on our minds very much. The theorists who support all of this, it's on their minds very much. And in fact, Adam Beardsley, the postdoc in my group, who just got an NSF postdoc fellowship, it's one of his aspects of his planned research is to start using one of these pieces, the 21 centimeter fast modeling engine, and bring into it predictions for it's focused for us, hence the name, but tie in also outputs that connect it to the galactic observations. Yeah. Things like Hera, the new radio array that we're all building, have the potential to actually take to tell a particular region of the sky, a few square arc minute region, or maybe even bigger, maybe tens of square arc minute region and say, that's probably an ionized area, or that's probably a neutral area, which is a whole nother way of connecting the two together. But that requires an array. Yeah. Yes?
Is the directionality of the antennas relevant?
The directionality, it would be, we don't treat it as relevant so much. We only sample the one active dipole polarization. We don't even do both. We need to go to different latitudes, so we just look straight up. So we're stuck going, if we want to look at a different part of the sky, we have to go to a different latitude to look at a different declination on the sky. But since we drift over the course of a year, we see the entire right ascension that would go over us, that part of, for that declination. The more individual samplings you can get on the sky, the better you can fit your model, because the 21 centimeter signature would be the same for this big global area. But your nuisance terms would be different. And so there's handles you can get, and there has been a theory paper by one of our close colleagues, Adrian Liu, on that. But for us, we're so much more worried about the fact that the beam of the antenna changes in in frequency. That is by far the most dominant concern for us. And the best way to have a well-behaved beam is to look perpendicular to the plane underneath it. And so we're pretty much stuck in that scenario. Yeah. Yeah.
What's the thermal distortion?
What's the thermal distortion? I don't have a number to quote for you. We have models of it. I can quote for you numbers on reflection coefficient variation over the course of a diurnal cycle, and so that's not going to be like 0.01. It's not going to be a normal unit. But from our standpoint, that's what matters, and it's about 0.01 dB out of our matched antenna, which is around minus 15 dB. So it's right at the level that we are able to measure, period. So it's not a dominant thing. And we only do all the nighttime observing and stuff like that. So it's actually less variation over the course of a one night period. So, but we do think about that. And you notice our antenna is out there exposed. We did paint it with the Goldstone paint, so it does, not get too hot during the day, but we're more actually worried about its thermal properties at night. Yeah, we've avoided the radome kind of concept, A, for simplicity, and B, we're so worried about anything that might have loss on the path of the signal, including before it hits the antenna, that we just didn't even, if we can avoid it, we're going to do it. Yeah. Although the radome would keep the kangaroos from sleeping under it, which would be an added bonus. So, kangaroos change the electrical properties of the antenna. Okay, just in case anyone didn't realize that. That's the why we care. Otherwise, we're happy to provide kangaroo homes like that.